Physics in the Flesh. Today we are going to be doing a power and change of energy problem. A 1,300 kilogram sports car accelerates from rest to 92 kilometers per hour in 7.2 seconds. What is the average power delivered by the engine? So in any question that involves power is always given by this formula, the change in energy over the change in time. And in this case, it's a car accelerating. There is a kinetic energy involved. Okay, so delta E, we can just call that delta EK. And delta T as well, our change in time, our time interval, the 7.2 seconds stated right there. Okay, so while I'm identifying things in the question, notice the question says the car accelerates from rest. Key point, V1 equals 0. You know what, even if you don't know what the question's asking or how to go about it, the second you see something like that, start writing it down. Starts from rest, is dropped, things like that, V1 is 0. Okay, so now delta EK we know is the change in kinetic energy. So that's EK2 minus EK1 over my delta T. And next you want to substitute your expressions for the change in kinetic energy. So 1/2 mv2 squared minus 1/2 mv1 squared all over delta T. Okay, so here's where that V1 equals 0 comes in handy. This is why we did that. If V1 is 0, V0 squared is 0, and 0 times anything is 0. So this entire piece disappears. So that makes things a lot easier. Okay, so for the next line, you see that half in the numerator. I'm going to do it so that the 1 stays in the numerator, but that 2 comes to the denominator there. Okay, so in other words, you're going to end up with mv2 squared over 2 delta T. Okay, so plug in your mass. The car is 1,300 kilograms. V2, okay, so V2, they gave it to us in kilometers per hour. So we're going to have to convert that. So I'm going to just leave a empty bracket here over 2 delta T, 7.2 meters per second. Okay, and while I do that, let me try to figure out what the V2 is in the correct units. Okay, so 92 kilometers per hour. Now, it's been a while since I did any conversions, but I did a lot of these in my earlier videos. I'll just briefly go over it again in case you haven't seen them. Whenever you're changing units, you want to multiply by 1. Okay, so I'm changing 2 units here, kilometers to meters and hours to seconds. So I have to multiply by 1 twice since I'm changing 2 things. Why am I multiplying by 1? Well, because if you multiply by anything else, it's going to change the question. And remember, you don't just have to multiply 1 as 3 over 3 or 16 over 16, because that really is going to do nothing for you. You have to put 1 as something that's going to help you. For example, the reason you can write 16 over 16 is because the numerator equals the denominator. But in this case, you're trying to get rid of kilometers, right? So let's say I put kilometers in the denominator and I'm trying to achieve the units of meters, right, in the numerator. So what ratio of meters to kilometers equals 1? Okay, so 1,000 meters is equal to 1 kilometer. So this thing is still equal to 1. That's what I mean by multiplying by 1. Now you're going to multiply by 1 again to get rid of the hours. Okay, so hours is in the denominator here, so I'm going to put it in the numerator there. I'm trying to get seconds out. What ratio of hours to seconds gives you 1? Well, I know that 1 hour is 3,600 seconds, right? This thing is still equal to 1. So honestly, guys, if you want, you can memorize that, okay, to get from kilometers per hour to meters per second, you just divide by 3.6, or vice versa, you multiply by 3.6. But understanding how to do stuff like this will help you later on when you have different units that you don't know how to convert necessarily. And this way you'll always remember how to convert it and where the strategy comes from. Okay, well, enough talking about that. Let's cancel out the hours, cancel out the kilometers. 92 times 1,000 divided by 3,600. Punch that in your calculator and you're going to get 25.56 meters per second. And that is precisely what I'm going to plug in over here. Okay, so 25.56 meters per second. And actually, I think that should be getting squared. So let me remember to put that squared in there. Punch all this in your calculator and you are going to get the power is 5.9 times 10 to the 4 watts. And that is accurate to the right number of sig figs. So there's the power delivered by the engine. Now, when you talk about cars or you hear about it on TV or even on Top Gear, whatever you watch, they don't usually quote the power delivered by the engine in watts, right? Because that's not really a terminology that we use. Usually people use something called horsepower, right? And so let's try to convert this to horsepower. It turns out that 1 mechanical horsepower is actually equivalent to about 745 watts. Well, 745.7, so 746 watts. Okay, so understanding that conversion, we're going to convert the watts to horsepower. Okay, so therefore, 5.9 times 10 to the 4 watts. We're going to divide that by 745.7 watts per horsepower, right? So if you do that, your watts cancel out and the denominator in the denominator comes up to the top. So pretty much dividing those two numbers, you're going to get about 79 horsepower, which is very low for horsepower. That's almost as much horsepower as my diesel Jetta has. Very low. Can't accelerate with that. And hey, who knows? Maybe this is a sports car from the 70s. Anyways, guys, I hope you enjoyed the video. I hope to see you in the next one, posted tomorrow at 12 noon, 116 Power 2. All right, guys, be sure to subscribe to Physics in the Flesh, by the way, if you haven't done so already. Otherwise, I will see you tomorrow. Hey guys, that's it for this episode. If you enjoyed it, be sure to check out some of my most recent videos posted over there on the right, which you can click on your screen right now and watch. Other than that, guys, I hope you enjoy the rest of your day, and I will catch you in the next video. Is the end screen too long this time? Wait, you're still recording? No! Oh. Gotta move that chair out of the way next time.